So one of the things you'll probably notice in this slide, notice how the stars are kind of changing in brightness. Well, stars do that, and they're called variable stars. So disclaimer, on the website I posted that I'm going to be talking about variable stars. That's not true. I'm not an astrophysicist, I'm not an astronomer like Don is and other people. So I can't really tell you all the cool physics involved with variable stars. But what I can talk about is observing them. And it's a very important citizen science activity that any one of you with a telescope or binoculars or even your naked eye can contribute to science. So, what are variable stars? So variable stars, as it says there, they're stars that change in brightness. A lot of people, they'll look up at the sky and they look and they think, well, these stars aren't changing. They'll see them twinkle and things like that, but they don't see them change in brightness, but they do change in brightness. They can range from thousandth of a magnitude, which is very, very slight, like if a planet is transiting a star. Or you can have as much as 20 changes in brightness, usually with cataclysmic variables or supernova or nova. So there have various ranges, like some will change in fractions of a second, others will take months or even years to change in brightness, or decades even for some of them. There are so many of them out there, and we're discovering them, especially now, all the time because of the sky surveys like SASN. SASN, in fact, I think recently discovered a bunch of variable stars that we did not know existed before. So they're very important to astronomy because variable stars are used as what are called standard candles, and we can talk about that in another presentation. But they use them as a way to determine the distances to like distant galaxies. So astronomers use this a lot. Plus it helps them understand the evolution of stars. By the way, this is my favorite shirt. If you can barely see it, this is what's called the HR diagram. I'm probably the only person in Ohio that has an HR diagram shirt. But,
I thought you sneezed.
Huh? Yeah. My wife saw this and she goes, "Did you get something on your shirt?" No. So there are two types of variable stars. We have intrinsic variable stars, and we have extrinsic, and I want to talk about each type. But the differences are the intrinsic variable stars is there's actual changes occurring with the star itself that's making it change in brightness. Extrinsic is where you have eclipsing binaries, where you have a dimmer star passing in front of a brighter star, or you might have planets, which we've been looking at lately, and Isaac has even done light curves on them, of planets transiting in front of these stars. So let's talk about pulsating variables. So pulsating variables, the actual star itself, you're going to see some expansion and contraction of the star. And when that happens, it actually changes the luminosity of the star. As it gets bigger, it gets dimmer. As it gets smaller, it gets brighter. And that's because of like the contraction and the expansion of the layers. Stars, when they start getting a little older, just like us, they start expanding and contracting. Especially when you go to
expanding.
Yeah. Expand. Yeah, that's right. We pretty much expand. The second point here, it can be radial or non-radial. So some stars, they blow up like a balloon equally in all directions. Others start stretching, especially if they're orbiting, or not orbiting, but they're rotating fast. So you'll see, we can't see this actually happen, but I can tell it's happening by spectroscopic studies and spin rates. But there are two types. There's the radial and the non-radial, where it's either contracting and expanding equally, or it's stretching out like a balloon.
Binary stars expanding, contracting, gravitational forces?
I'm sure there are some, just like the Earth's tides will stretch and stuff like that. It depends on how close the binary is. So C5s are probably one of the most popular variable star around. Usually the period is between 1 to 70 days, about 1 to 2 magnitude difference. There are type F, or if anybody's not familiar with the types of stars, there's a cataloging or a grouping of stars into various types. And it's O, B, A, F, G, right? O, be a fine girl, K-M. The mnemonic is O, be a fine girl, kiss me. Or O, be a fine guy, kiss me. Sorry, I just had to make it. So now these stars are very important because this is the kind of star that they're going to be looking at in other galaxies. In fact, they were looking at C5 variables in the Andromeda galaxy, and that is when Hubble and other astronomers at the time were figuring out, wait a minute, the Andromeda galaxy is pretty far away. They knew this period luminosity relationship then, and they used these C5 variables in the Andromeda galaxy to determine, wow, this thing is farther away than we thought. They didn't realize that these galaxies that they were seeing were outside of our own galaxy. But pulsating variables like C5s enabled them to figure this out. So this is an example. Notice I'm not using a green laser pointer. Yeah, I stopped by CBS to pick up one of these because I knew that.
Thank you.
You're welcome. I'm going to talk about what these are. These are called light curves, but this is a typical light curve of a variable. Now, one of the interesting things about variable stars is that they have their own fingerprint, right? Not only spectroscopically, but also the way their light curve is. So you could say, oh, that looks like a C5 variable by the way the light curve is presented. And Delta Cepheus, which is actually out tonight, is the prototype star. A lot of times you'll have a prototype star, and that's what they name them out there. So our Lyrae stars, usually you find these in globular clusters. In fact, the first slide that I showed with the pulsating stars in it, those are our Lyrae stars. The Class A white giants, they don't have as many, or they don't change in magnitude as much as other types of stars, and their period is not very long. So we're talking less than a day up to a day. Like I mentioned, it's they're found in globular clusters. They're older and they're less massive than the earlier of these C5s. I'm going to run through these. Don't worry, there's no quiz. Just get the impression that there's a lot of you were upset there was no quiz, right? There are so many different types of these stars. I'm just going to blow through them because what I want to do is I want to get to an actual part of the presentation where we actually get to estimate a variable star on the slide deck. So there are RV Tauri stars, period 30 to 100 days. They can have an amplitude of 3 magnitudes. They're yellow supergiants, which by the way is my favorite class of stars because stars don't last in the yellow supergiant phase very long. 10,000 years, I think, roughly. That's how long that these stars, which 10,000 years is like a second to us, to a star. They don't last very long in the yellow supergiant stage, so it's my favorite star around. So they have a variation between alternating deep and shallow minima. Periods are defined as the interval between 2 of the deep minima. So you may have like a shallow minima, then a deep one, and then another shallow that kind of looks like a pulse, doesn't it? That's the period that they talk about, are the deep minimas. So some of them have weirder, longer cycles over top of the cycles that we normally see. So this is another popular class of pulsating variables. They're called long period variables. Polaris is C5. That's right. Sorry. Mira is the most famous example of this type of star. And by the way, Mira is short for miracle. They called it that because they knew that it was changing brightness. And if you have a star changing in brightness by 5 magnitudes, that's a lot. You would notice that. They're all red giants. Between C and S are new classes of stars. C stands for carbon star. I don't know what S is, but it's just different spectral lines of how the star is made up, but they're all basically red giants. And their period is a lot longer too. Then we have some real weird variables that we're trying to get our hands around. There are semi-regulars like Z, Ursa Major. The amplitude isn't very big, but they're giants and supergiants, showing periodicity. Can't say that. Periodicity. I never said that I could talk right. But the key is you can see there's some irregularities, like in the length here. It's kind of longer the peaks, it looks semi-regular, but there's still some weirdness going on. So these are the neat ones, the violent outburst one, cataclysmic variables, usually caused by like a white dwarf getting atmosphere off of a companion star, collects onto the white dwarf, and then it explodes as it gets to a certain point. The Chandrasekhar limit. Yeah, I know a little bit of the physics. It's neat to study that stuff. But so, anyways, so these types of variables, which include the novas and supernovas, they're pretty interesting. Our first one's going to be a supernova. So one of the most famous ones that's happened recently is supernova 1987A that exploded in the Large Magellanic Cloud. This is the key right here. The amplitude of a supernova is 20 plus magnitudes. When one supernova goes off and you see them in other galaxies, that outshine the combined light of all the stars in the galaxy. Imagine that. That's a huge difference in brightness. When a star outshines the rest of the galaxies. One of the neat things about supernova, I know many of you probably already know this, but things like gold and uranium and all those heavy elements, they form in these exploding stars. They don't occur naturally because stars generate elements and things like that. They only occur because supernovas cause them. So that's one of the neat things about supernova. The nova is the little cousin of the supernova. Usually these aren't stars blowing up, but as you can see here, it's like a sun-like star orbiting around a white dwarf. The atmosphere comes off, gathers around the white dwarf, and as soon as it gets to a particular point, then a thermonuclear explosion occurs, and you get the nova. So this is one of those novas, and these can reoccur over, they can happen more than once. This particular light curve is from Nova V1500 Cygni. So here's another type of cataclysmic variable. You might have an outburst from 5 to 20 days, and the magnitudes are pretty noticeable between 2 and 6. So the periods are about 30 to 500 days. Again, this is a prototype star in the constellation Gemini. You can see the light curve here as it kind of bursts out. Well, I'm going to say this really bad. Z Camelopardalis.
Yes.
Latin is not my strong point. So these type of stars, they do have a large range. It's kind of like it'll sit there and then it'll sputter and then it'll brighten up. It'll sit there and sputter and brighten up. You can see the light curve is very erratic. You see how it looks like it's starting to have like a little period of stability, or not stability, but irregular changes in brightness. Then it kind of stays there, and then it goes back, and then it kind of dips, and it looks like somebody should go to the heart doctor and get some medicine. Symbiotic stars is basically close binaries. Most of the time it's a red giant with like a hot blue star, and they're embedded in nebulosity. The light curve, it's kind of like a nova, but it's not as long term between each nova as outburst. This is an interesting star, only because one of my favorite astronomers, who's an Ohioan, which I will be talking about soon. This is one of his favorite variable stars. Our corona borealis will stay at a particular brightness, and then it'll dim all of a sudden. It'll stay dim for a while, then it goes back, and then it'll dim again, and then it just stays the same brightness for decades. So the one time he observed this star for many, many years, and then the one time he didn't observe it started dimming, and he wanted to catch it in the act. So it was very upsetting to him. So Algol is the most famous example of an eclipsing binary. The eclipsing binaries are simply we are in the plane of orbit where the star or another star is eclipsing it, and we can't see the other star, it's too close, but we know it's there because spectroscopic studies show a different spectrum shift as it orbits, but also the brightness changes. There are some stars that have very large, we call them sunspots on our sun, but on stars we call them star spots. But they're so big, especially on M-class dwarfs, they're so big that as the star rotates, this large star spot gets in the way, dims the star. So naming variable stars is quite interesting. The IAU appoints the names as they're discovered. So the assignments are made in the order that they are discovered in a particular constellation. If the star has a Greek letter name, if you ever heard of like Alpha Orionis or something like that, it's still referred to by the Greek letter. Hey, I said Alpha Orionis. Alpha Orionis is Betelgeuse. Don't say it 3 times. It's a variable star. It's a red giant that is changing in brightness, and you can actually track that. So otherwise, it starts at R, and then it goes R, S, T, U, V, W, X, Y, Z. Now, it starts over again at Z. You go R, 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 S, R, T, R, Z, all the way up to Z, Z. So after Z, Z, we go to A, 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 B, on to Q, Z. We don't know why letter J is omitted. So we can go up to 334 variables using that naming convention. After that, you'll start saying V or 335 for the first one after all of them have been exhausted. Cygnus, which is a constellation, has lots and lots of variable stars, so they're way beyond 335. So the letters are combined with the possessive Latin form of the constellation name, like SS Cygni. The prototypes are named that as well. So why does the naming scheme happen? Had to be a freaking German. The German engineers always like to say the joke. Have you ever seen a windshield? If you're German, I'm not trying to offend you. But have you ever seen a windshield wiper on a Mercedes-Benz? Someone came up with the bright idea to make one windshield wiper work for the entire windshield. So in order to make that happen, because if you had one windshield wiper, it would go above the windshield and go to the other side. So what did they do? They made it so that the whole thing goes down and goes like this. Well, if you're in a rainstorm, that thing stinks because you can't go that fast. So no wonder it's a complicated naming scheme. Actually, I think he was Austrian. So naming variable stars. So he started with R for 2 reasons. Lowercase letters in the first part of the alphabet were already used for other designators. So you'll see some of that. He believed that variables were rare and that they would never, ever need more than 9. Just like we never need more than 100 megabytes of data, right? Still, it's a mystery why J was omitted. Now, there are other naming conventions. There's the Harvard designator. It's a group of 6 numbers and a sign that gives the variables approximate coordinates in epoch 1900 when they started this. The first 4 digits are the right ascension, followed by a plus or a minus, and 2 digits for declination. For example, our Leo is 0942 plus 11. You'll see that a lot in certain scientific publications. So why do we observe variable stars? Well, we want to determine the long-term behavior of the star. We want to provide professional astronomers with data so they can analyze this behavior. We can schedule, because we have a period that we know of, we can schedule observations of certain stars at certain times. We want to correlate data between satellite and ground-based observations, and we can make computerized theoretical models of variable stars. And it helps us with our understanding of stellar evolution, things like that. So here's Leslie Peltier. He's the guy that liked our Corona Borealis. He was born in 1900 in Delphos, Ohio. If you haven't read this book, I highly recommend it. It should be in every amateur astronomer's library. It's called Starlight Nights, Adventures of a Stargazer. Neat thing about this book, if you ever get bored about observing the stars, you're like, I don't want to get my telescope out anymore. Or if it's cloudy nights, like in the wintertime, this is a great book to read. It will reinvigorate your love for astronomy. And also, he built this famous observatory. And this observatory is actually in the park over there in by Dayton. What is it?
John Bryant State Park.
Yeah, John Bryant State Park. What he did, he created an observatory where he sat in a chair. He could turn the observatory around so he could track the stars. So the telescope in him would turn the whole observatory would turn, and he got it from like one of his relatives worked in the merry-go-round business, and he got some of the parts to do that, to build it. He was a great amateur telescope maker. Yep. All right, so we have the AAVSO, the American Association of Variable Star Observers, founded in 1911. It's got members from 45 countries, and we have, this is an old slide, there's a lot more than 12.5 million. So this is still true, it's over 12.5 million. It's probably over like 20.5 million. There are various types of observing programs. So there's a couple different types. There are two main types. We have the visual, which we use our eyes, and we have CCD or spectroscopy type programs. It gets more advanced as you go down the list. But the one I'm a part of is the visual observing program. It's the largest component of all the observations in the database. There's more than 5,000 stars to observe now, but you cannot run out of stars to observe. One of the neat things about variable stars is they become a little more personable. You get some of your favorite stars, like my favorite stars are Leo, because that was the first variable star I ever observed with. And it's really neat to look at, because I've seen it change in brightness, not instantaneously, but over time, as I track it, you can actually see the curve start to form. And it becomes kind of like an old friend, as Leslie Peltier would say. He's just like, you go back and see his old friends. You go out at night, so his telescope actually went to his observatory. And he looked at these stars, and it looks like you're getting dimmer again. So it's kind of like visiting an old friend, is what he would say. Eclipsing binaries, that's if you're into finding out the minima of when a star is being eclipsed. That helps them find out the masses of stars, because they can calculate that based on how fast the star is revolving around, and if it's speeding up or slowing down. Our Lyris stars, those are the ones that were in the globular cluster. There's the Nova and Supernova search program. There's a lot of, Assassin. There's a lot of automated programs going on right now where robotic telescopes are taking pictures of the sky, and it allows them to find the supernova. Photoelectric photometry program, this is like the old way of doing it. They use photoelectric tubes. Not a lot of people use this anymore. The 4-color CCD program, that's really what they're using nowadays. And I'm about ready to start getting into that. So, this is where it gets kind of fun. There's a little bit of audience participation. Yeah?
If you're part of that program, what do you do with the data?
I'll get to that. Yep. So, I'm going to do that at the end of our audience participation. So, how do we make visual observations? First of all, the eye is very good at, we may not be precise, but we're very good at comparing things, right? Good, bad, bright, dark. And we can interpolate data based on two extremes. Well, that soda is sweeter than that soda, but it's not as sweet as this soda. We're very good at doing those kinds of things. So what we do is the same thing as with variable stars, is we take stars of a known brightness that they verified that the brightness is a certain magnitude, and we say, okay, is the variable star brighter or dimmer than that star? Oh, it's dimmer. Okay, is it brighter or dimmer than this one? Well, it's brighter. Okay, well, it's in between these two known magnitudes. Then you can refine that if there are more what are called comparison stars. So we interpolate this kind of information all the time. Yeah, so here we go. An example, when a gas gauge is between empty and reporting, the most important telescope you own is your eyes. A good telescope, a good finder, a pair of binoculars works. A good star atlas to help you get to where the variable star is. You need a variable star chart and something to record your observations. Notebook paper is just fine. Or your iPad. So to get variable star charts, you can get star charts, or variable star charts in various scales. Some scales are pretty broad, like if you're looking at Betelgeuse and you're comparing Betelgeuse to a bunch of different stars. Or you can get them very refined if you're using like a CCD camera with some dimmer stars. Scale is determined by the equipment you're using, and you go to a website to generate these variable star charts dynamically. And there's the URL. And then every star chart from the AAVSO, the variable star is always designated by that symbol. And we're going to see an example. So here are the different scales. I'm not going to read them all, but you'll see, I want an A scale chart, so you would use that for binoculars or a finder scope, or like a smaller telescope, like a 60 millimeter telescope with low magnification, AV as well. And then you have stuff for smaller telescopes, larger telescopes, and then G is probably the one that we don't use very much. I mean, look at that, arc per millimeter, 2.5 arc seconds per millimeter. So the way you do this is what it looks like on the AAVSO star chart. It's free. You can generate as many star charts as you want. You can save them as PDFs. You can print them up. You can wallpaper your walls. This really. So the way you do it. So this particular example, I'm doing R Leo. Use that single letter designation. You type in Leo there, and you say I want it for visual. I want chart. Rarely do we want photometry. And then you say plot chart. Now this isn't our Leo, this is W Cygni, but this is what it comes up, this is what it looks like. You'll see here, that's a variable star, but that's not what we're looking at. That's V1339. Remember that V number? We're already up to 1,339 variable stars in Cygnus. Why do we have all these variable stars in Cygnus? Come on, astronomers.
A lot of stars.
A lot of stars, that's right. So Cygnus is in a very dense, the constellation is in a very dense region of the sky where there's a lot of stars. So that's why we have that high number. But this is the one we're looking at, WC. See all these other different stars with numbers? What that is, these are the magnitudes. So this particular star here, 40, that is a magnitude 4.0. Now, notice that they're not using decimals. Why do you think they're not using decimals?
It looks like a star.
Because it looks like a star. Is that a star or is that a decimal? So they never use decimals for the magnitudes. So what you do is you say, oh, okay, well here's the star. Is it brighter or dimmer than that? Well, it's dimmer. Okay, is it brighter or dimmer than this 5.4? It's brighter, so it must be between 5.4 and 4.0. And you use these other stars to interpolate what you think the magnitude is. So here's where we start trying this ourselves. So what we need to do, magnitudes of comparison stars are shown in tenths, so that we're not worried about hundreds or anything like that. We've omitted a decimal for clarity. We see here 6.4 is really 6.4. And then big dots are brighter, just like a regular star chart. Big dots are brighter than the smaller dots. So if this is our variable star, and these are our companion stars, let's go through our experiment. So, is this star brighter than the brightest star, 5.1? What do you guys think? Do you think that's brighter than this or dimmer? It's fainter. Right? All right. So we know it's not 5.1 or higher. So, is it brighter than the next brightest star, 6.1? Do you think it's brighter than that one? Think it's fainter? All right, how many people think it's fainter? How many people think it's brighter? How many people think it's the same? All right? So this is an interesting experiment. I'm actually doing crowdsourcing with you. It's fainter. All right, now, next one. Is this brighter than the 6.4?
Yeah.
How many think it's brighter? How many think it's dimmer? How many think it's the same? All right? Definitely brighter. So the variable is brighter than 6.4, but it's fainter than 6.1. So is it halfway in between? Is it 6.2 or 6.3? What do you think?
6.2. Yeah.
Really, it's based on what you think it is. It's your gut feeling. Okay. So the beauty of this is that you'll get better with practice. You'll be like, nah, that's really more of a 6.3 than a 6.2. To be honest with you, don't worry about it. Put what number you want in there, because what they're going to do, they're going to take thousands of observations and average them together. Because of that, they will be able to get closer, they'll get greater precision with the more observations that they have. right? For visual astronomy, rarely does anyone get better than a 10 for visual observations of variable stars. So really just go with your gut. So now we got our estimate. So what do we do? So I like this statement. I got it from one of the variable star manuals. The number can never be too exact in science, especially astronomy. But all measurements are really estimates to a certain precision. My scientist friends in here, would you not agree?
Yes.
It's all about precision. The trick is understanding what that precision is. So here's an example of a light curve. So this is our Leo, my favorite variable star. And one of my observations is actually in here. I just don't remember which one it is. I forgot that you can actually highlight your observation in the light curve. So you'll see here, there's a lot of guesses. I mean, there's some outliers here. I mean, there's some real big, you know. So if you understand statistics, they have like standard deviations and all that kind of stuff. So that's what they're doing. These are probably outside of the standard deviation of these estimates, right? But all of this is within the standard deviation. And what they can do is they can plot a line here to get pretty close to a tenth, even more of a magnitude based on all these estimations that everyone is submitting. The important thing is we need as many observations as we could get to get a refined number, a refined enough number for scientific analysis.
Looks like it was cloudy for a few days.
Actually, what that means is Leo, the sun was in front of Leo. Yeah. So, yeah, no, you'll see like on anything Ursa Major, you won't see that break because at this latitude, we see Ursa Major all year round, right? Well, most of Ursa Major, not the lower parts of Ursa Major. But for things like Leo or Virgo, where we don't see it for half the year because the sun's in front of it, that's why you see that break. So you'll see a lot of star charts or light curves. You'll see a break, and you'll see it come back, and then another break. So to submit an observation, you need some key points of data. And this is where we're getting into how you submit it. First thing, you need the name or designator. You can use either the RLEO or the Harvard designator. Either one will work. You want the date, time, and universal time. You want the estimate, that's the number you came up with. You want to include the companion stars, and that's very important, so they know what you use to interpolate your data. They want to know the chart date. All these charts have a date associated with it, so they can go back to that chart and see why you came up with that estimate. And you can submit it via something called WebObs. PCObs is no longer around. You can email it or fax it or even phone it. Nobody does that anymore. Most of the time, people will use WebObs. And I'll show you what that looks like. So before you even start doing a variable star program, you have to register what's called an observer code. Mine is HJS. And you'll get an observer code. It might be something way cooler than HJS. You will not get your initials. It's randomly assigned to you. But that is your observer code for life. They'll never remove that away from you.
It's closer. It's like mine have CZ.
Oh, is it?
CZ.
Yeah, they'll try that. You know?
Yeah.
But Hissong, Jason, I don't even know what S means.
Spot.
There you go.
Sir.
Yeah, super. Yeah. All right, so you tell it which type of observation. We're going to do a visual observation. Put in your observer code, because that's automatically filled in because you log into the website. You do not have to be a member of the AAVSO to do this, by the way. It's completely free. Because they really want the data more so than your money. But they will take your money. Here's your star identifier, the date, time, magnitude. The first comparison star, you need more than one. The second one, there's your chart ID. Now, here's these component codes. This really, you can use it for like the filter you're using. There's a blue filter, there's a visual filter. This view means unfiltered, which they really don't care much about the unfiltered, but it could be useful when trying to determine the range of where the estimate could lie in. And any comments, you submit it, and then you're done. So there is a list. If you go to that address on the web, there's a list of all these stars, and I've done some of these. where you can go in and use small telescopes and binoculars to start doing a variable star observing program.
Do they not take into consideration observing conditions?
Yes, they do. They do. Actually, thanks for bringing that up. So some of those codes that I was showing you they do indicate observing conditions. Yeah. So I don't remember all of them.
U is actually a filter, Vincent.
Is it? I thought it was unfiltered.
It's a filter.
Oh, that's right. It's ultra.
UVBR.
Yeah. That's right. Yeah. So, and then you can click on here and it says, hey, what do these codes mean? Like there's one where you can say uncertain, like you're not totally positive. The other one is if the moon was out, causing your estimates to be off. And one of the things when you're doing variable star observing, this just comes from experience, red stars are harder to estimate than non-red stars because of the way our eyes interact with red light. Red stars, I might get this backwards, look brighter to us than normal. So what I do for red stars is I defocus it, right? And I keep defocusing it until it disappears compared to a star that I think is brighter than it. And when it disappears, but the one that's brighter than it stays there as you're unfocusing it, you go, it's dimmer than that. So you put it back in focus and you can try it going the other way. Then, when you're trying it with the dimmer star, you start unfocusing it until the dimmer star disappears, and if the red star is still there, you know it's brighter than that. So it distributes the light evenly, and it helps our eyes see it more. So one of the things I'm going to start getting into, especially I'm an iTelescope member, and iTelescope, and there's a tool that AAVSO uses called VFOT. It's just kind of fun to say, VFOT. It interacts, so you can actually take the data that you get from iTelescope. If you're not familiar with iTelescope, it is an internet subscription-based telescope network from around the world. They have telescopes in Spain, Australia, California, and New Mexico, I think. And there's even private observatories that uses the interface, but only the people who own it. You could probably do that. Anyway, so you can use this. You can do either iTelescope or use your own CCD system, which I plan to do both. But you need the absolute minimum that you need is something called a V filter, and it's kind of a green filter, and it's at a standard bandwidth so that we can take all these observations and make sure we're to the same playing field. And there have other colors that you can use. But iTelescope has a standard set of variable star observing filters. So in order to do that, you got to calibrate your equipment to know what you're dealing with, because not everyone's equipment is the same. You have different quantum efficiencies of your CCD camera. You have different optics. You know, you might have an achromat or an achrochromatic telescope, which really doesn't matter much, but it does influence how much light is transmitted through the lens. So what you do is you take a series of different lengths of images, exposure, thank you, and you use that to try to get to a particular range of numbers. And I forget what it is. You probably know better than me. You got to get to a certain ratio so that your data is above the signal, or the signal to noise ratio is at an acceptable level. A lot of times people use M67 as kind of the prototype globular cluster because it's very well known. They have all these different spectra or different colored stars that you can use for the different filters. I just found about this today, and there's these things called Landolt and Hendon fields that are standard areas of the sky where they know the magnitudes for various stars in various colors. And then this is VFOT, by the way. This is where you have all your images. You can use this to help you estimate stars and compare them to known magnitudes in software, and it's cloud-based. So here's an example of Landolt field. So this is the field itself. These are your your standard estimates. So you take this and you say, okay, this star is supposed to be this. You calibrate your software to match that. And then you have various types of colors. Or various magnitudes here in different, so there's your V filter. So to get started, like I mentioned earlier, you can go get your observer code for free. Just go to AAVSO. They love it when new observers get involved. You can download these various guides, like here's the one I want to start reading, the CCD photometry user guide. It's awesome, it's free. Here's the one for visual observing. You can go get some charts. Our Leo is a good one to start with. Right now, the perfect star to start with is our Scutum. It's our Scooty, actually. The possessive. This is kind of funny to say Scooty. So our Scooty is one that's up right now that you can use to start your observing program. Start observing, start submitting your observations. This is great because there are teachers in here. One in the back. This is a good thing that you do with students to get them involved in something where they can actually start contributing to science. There's a big initiative where they have all these people around the world. They crowdsource scientific data analysis to just people like us. In fact, crowdsourcing has been around since the 1900s because the AAVSO has been doing it since then. Now we have the power of the internet to allow us to do things like, hey, we can look at light curves for planet transits. We can look at various galaxy types, because they're trying to catalog all the galaxies out there. So AAVSO is the oldest crowdsourcing platform for people to be citizen scientists. And I hope we're... Oh, good, 9:30. That's what I was trying to...
And can you do that? Can you do this from the city, Jason?
Yes, you can. I'm glad you did. I live in Hilliard, and I started doing this from my driveway. Like I said, my first star I looked at was R Leo back in 2001. I remember it was April 9th, 2001. April 8th. It was the first time I did a variable star estimate. A lot of these stars that are easy to see with binoculars or small telescopes you can look at and do in the city. A lot of people do that. You do not have to be at a dark sky set to do this program. So, any other questions? Yes, ma'am?
How often do you do it, and do you turn in the data immediately, or do you turn in the data in the
It really depends on what you want to do. I usually do it the night that I do an observation, just because I forget things. But many people, they'll just do like a big massive upload for all those observations that they've done. It's really just your style. Yeah. But, what they do is there's a process. They just don't take your data blindly. They validate it. They go through and they validate, make sure that it's not, because they want to make sure that you're putting star estimates in there with the appropriate comparison stars. Like you may have put an estimate in there, and you have comparison stars, and they're like, there are no comparison stars that are on this star chart. So they'll throw that data out. You might have mistaken it. Thought you were looking at R Scooty, but you're really looking at W Cygni, and you mess up. So that's where they do the validation process. So that takes time before they actually publish the data to be used by scientists.
So it's kind of interesting because, they have them as unverified, verified, and still you actually have some outliers in there. So there must be some...
Yeah. It's not like they'll show that in the light. So the light curve that I generated, I generated this light curve. That light curve, this isn't for scientific published data. This is just what the databases say. They're saying that these estimates here, and the V means that somebody used a V filter to do those estimates with the CCD camera.
Well, the difference is, looking at the bottom, that some of those are fainter than, which means that the star was below the instrument level to see. So they're basically someone just submitting a measurement and saying, it was fainter than I can see.
Yeah. But you'll also notice that none of the outliers are filled in. See? Now they haven't got to, at the time I generated this, they have not gotten to the point of validating this data.
Right.
The ones that are filled in are validated.
I validated, yeah. And that's basically what I was trying to say. There's still some, most of the ones are unvalidated.
Yes.
But you still have some outliers in there.
And what someone like me will do with this is we can weight the observations as well. as far as their effect on the overall distribution of the light curve and that. We could reweight them and still use them as somewhat valid estimates.
Yeah, but the weight basically.
Yeah,
moving over a little bit.
exactly.
Yeah, so then, and there's a place on the AAVSO website where you can actually get the validated data for use in scientific publications. You would never use this for scientific publications. Yeah,
How often do they publish the
you
final?
know, I don't know.
Like
I don't
every
know.
6 months or?
I don't know, actually. I've never needed that data. You probably know better because you use it.
Well, I mean, essentially when you put it up there and, then they just do a basic check to see, if you're using the right comparison star or right star, put in the right information. It will go into here, but then the validation process is a little bit more involved.
Right. I would never think you would cite this information.
Not that. No.
Yeah, right.
So is there a point in time where they actually publish it, say this is the data for that time period? Or?
That's internal to them. I don't exactly know the process.
You can actually go on the website and do a search for your favorite variable star, and you can get published with the data. Any other questions? As you can see, it's not too difficult to do this. When I first got into variable stars, I thought, that's something I can never do. But then I realized it's like, it's very easy. What's the guy's name? Vic. Not Vic. I forget his Vic. No, he plays the flute. I've run into him before. Vic Wolf? Yeah, is that right? Yeah. No, that's Vic Wolf. Vic's like, what do I do? Now, anyways, he's the one that got me into it. He's a former CAS member.
Oh, no, Steve Wolf.
Steve Wolf, thank you. Steve Wolf actually got me into doing variable stars. And what he used was a freaking parabodometer.
I see where you got
That's
to
what he
Vic,
did.
though.
He'd have a start.
I see where you got to Vic though.
All right.
Yeah.
Any other questions? It's clear outside. There's a nasty rumor going around. It's not?
We haven't said what you said.
High altitude garbage.
I'm sorry.
Cloudy. 6 o'clock, did it cloud?
Yeah, everyone's doing this. I trust Chance.
Welcome to Ohio.
Well, if you have any questions, you can email me. My email address is on the webpage. I'm the webmaster for the Astronomical Society. Just look me up there, and I'd be glad to answer any questions.